Alright, we are still in Calculus 1, Chapter 2, now Section 4, where we're going to start talking about the precise definition of a limit. This section not only talks about the limit with a precise definition, but also the limit as we approach from the left and from the right, and if you're evaluating a limit and the answer ends up being positive or negative infinity, this one section also addresses that. And I'd like to look at some homework problems with you. So what I'm going to do is break this section up probably into a little three-part series. We'll start out just talking about the limit, then we'll cut, and then the second part 2 we'll talk about the limits as we approach from the left and from the right, and limits that end up going to infinity. And then I'll make a part 3, which will be just looking at some example problems and talking about setup and approach for problems by looking at a homework assignment. But first, let's get into our precise definition of a limit. And actually, I don't want to start there. I want to start down here. Sorry for all the scrolling. These are notes that are provided by Cengage in conjunction with WebAssign and Stewart's Calculus book, 8th edition. And this is an example, sort of, or a problem that was provided for us to do some practice. And what I want to show you here is a very key aspect of what we're going to be talking about in this precise definition. And what's happening here is actually, is there a limit statement somewhere? There's not. That's okay. What's happening in this diagram is vertically you can see on the y-axis you see this y value of 2, and then above and below it are these two other numbers, 2.5 and 1.5. And the difference, or the distance, so to speak, from 2 to 2.5 and from 2 down to 1.5, there's a consistent difference of 0.5 there. And this value of 0.5 is an epsilon value. There it is. Epsilon, that's lowercase epsilon, is being given to us as 0.5. And we've also been given this blue curve, which is our function f. And the task that we're trying to accomplish here is, if we have this sort of target value, target y value of positive 2 in this case, and we want to plug in x values into our function that give us y values that remain in the neighborhood of positive 2, let's say within plus or minus 0.5 of positive 2, then what x values would we be allowed to plug in order to make sure that the resulting y values stay within plus or minus 0.5 of the number 2? We can answer that question by looking at this graph carefully. If we take the lower of the two available, sort of the lower bound for our y values, which is 1.5, and we draw this horizontal line over to our curve, we hit the curve at this point. That point has a y value of 1.5, and very nice, this diagram, this graph shows us that its corresponding x value is 2.6. And if we went through that same process for this upper bound for our y values of 2.5, and we draw a horizontal line, we come over here, we catch this point on our curve, and grateful again that we have been shown that that point's corresponding x value is 3.8. So what we're seeing is that if we use x values that are between 2.6 and 3.8 and we plug those into our function, as long as we're using an x value that's in there somewhere, we will end up with a y value that is no more than 0.5 away from 2. That's nice. Now vertically, I showed you that that epsilon value is 0.5. We're starting with that y coordinate of 2, and then we're going up or down 0.5 on the y-axis. We'd like to do something a little bit more similar to that here on the x-axis. Now this number of 2.6 is 0.4 away from 3, and this number of 3.8 is 0.8 away from 3. So we'd like to be able to say, or if somebody asked us, well, what x values are you allowed to plug into the function in order to stay within plus or minus 0.5 of a y value of 2? We'd like to say, well, you've got to stay in the neighborhood of 3. And they say, well, what kind of a neighborhood? Plus or minus how much? We want to be able to answer that question with one number. And we can't use plus or minus 0.8 because if we move 0.8 to the left of 3, that would put us at an x value of 2.2, and an x value of 2.2 would take us up to this point on the curve, but that point on the curve doesn't have a y value that keeps us in the desired range of y values. So we can't use plus or minus 0.8, so we're going to use or say plus or minus 0.4. Now if we use the plus or minus 0.4, if we come over here to 3.4, that brings us up to our curve here, and that slides us over to a corresponding y value of maybe 2.3. Well, but we're not utilizing all of those available y values. It's okay. We just need to find one horizontal plus or minus amount, in this case 0.4, that keeps us within the vertical constraints or the y value constraints of 2 plus or minus 0.5. Yes, we lost some y values, but it's okay. This one value of plus or minus 0.4 in the x direction is going to safely keep us within our constraints in the y direction. Now if we went through this entire process again, and specifically we found this 0.4 and this 0.8 down here, and the arithmetic has been done for us over here on the left, will we always choose the lesser of those two horizontal values? And the answer is yes. We would always end up choosing the lesser of those two, because it tightens up our constraints horizontally, which guarantees that we end up where we want to be, near our target value in the y direction. Alright, that introduction and description took 8 minutes. Now we're going to spend many more minutes talking about the other scenarios that we can run into and some more of the details of this process. And this was page 30 of these provided notes. I'm going to scroll again, except I'll pause this time up to the top, and let's take it from the top. Alright, let's take it from the top. So, Chapter 2, Section 4, Precise Definition of a Limit. And then there's this first slide. It's too specific and too general, and it's just confusing. So, I want to come into this example here. This is a good one. And I've already circled something. Don't need that yet. So, there we go. This initial example, or this sort of second example, is a piecewise function, and wherever our x values are not equal to 3, which is most of the time, we would end up taking those x values and plugging them into this expression. If our x value happens to be 3, then our function is going to return a y value of 6. But because I'm going to be evaluating the limit of my function as x approaches 3, I don't really care what's happening when x equals 3. I care what's happening as we get really close to it. So I'm more concerned with x values like 2.9, 2.99, 2.999, right? If here's 3 on the number line, I'm concerned with 2.9 and 2.99 and 2.999, maybe 3.001, 3.01, 3.1. And as I take x values like that are getting closer and closer to 3 from the left, as I take x values that are getting closer and closer to 3 from the right, and I plug them into, well, I'm really plugging them into here, I would find, if I made a table of values, that my y values trend toward 5. And so we would say, intuitively, that our limit of f of x as x approaches 3 is equal to 5. Notice that when you actually arrive at an x value of 3, the y value is 6. Do we care? We do not care. Doesn't matter. We're only concerned with what's happening in the neighborhood. So what? Well, we're going to sort of adjust the game a little bit. The new task is, we can't just randomly or somewhat randomly choose x values that are near the number 3 anymore. Now we have to choose more thoughtful x values. We want to choose x values such that when we plug them into this particular function, we get y values that are near 5, near this limit of 5, but within 0.1 of the number 5. So our y values, our resulting y values, have to be somewhere between 4.9 and 5.1. Which x values are going to facilitate that? We could draw a graph, just like the very first example that I showed you, and then we could take our horizontal lines from 4.9 and 5.1 and draw them across and see where they intersect our graph, and then we could bring them down to the x-axis and then choose the lesser of the two differences. Absolutely, totally could do that. What we're able to do here is, I'd like you to realize, and it's worth taking our time to get acquainted with this process because we're going to need it again later. The distance from whatever x value we choose to the number 3 is equal to the absolute value of that x value minus 3. 2.5 minus 3 is negative 0.5. But I would never say that something is negative 0.5 away from something else. So if we take the absolute value, that gets rid of that negative sign. Similarly, the difference in our y values. Here's our y value. Here's the limit of 5. That's also a y value. The difference between them. And if we take the absolute value, it's more like a distance because it's a positive number. And our problem, our challenge, is to find a number delta. That's a lowercase Greek letter delta, which usually represents change or difference. We need to find a lowercase delta such that the distance between our x value and the x value of positive 3, the difference between those is less than delta, so that the resulting y values have a distance that's less than 0.1 away from our ideal y value, our limit value of 5. So the only thing that we don't know in this statement with a bunch of red arrows under it is delta. And that's what we have to try to find. Now something, we're never going to be using an x value of 3, which means that x minus 3 is never going to equal 0, which means that the absolute value of x minus 3 is always going to be strictly greater than 0, which is why we're allowed to write this part of this statement. So now we know that the difference between our chosen x values and 3 this 3, the 3 that our x values are approaching, So now we know that our x values are going to be within delta of that x value of 3. This number, the wiggle room that we're given in the y direction, again, is our epsilon value. And then something magical happens. The statement that we're looking at that I circled in red toward the top of the screen right there is now appearing here in the middle of your screen. I'll leave it on there so you can compare them. Here's the 0, here's the less than, here's the absolute value of x minus 3, here's the less than, and then all of a sudden delta is not just a delta anymore, it's epsilon over 2, which happens to equal 0.5, or 0.05. Why in the world did we divide epsilon by 2? The short answer is that if you're working with a linear expression, like 2x minus 1, your delta value is going to end up being epsilon divided by whatever this leading coefficient is. In this case, it's a 2. It has nothing to do with capital L being 5. It has nothing to do with the fact that x is approaching a lowercase a value of 3. It only has to do with that leading coefficient. We're taking epsilon, we're dividing it by the leading coefficient, and that's giving us a delta value of excuse me, 0.05. We know what our function was, 2x minus 1. This is the difference in our y values. Here's our function of 2x minus 1 minus that capital L value of 5. Combine like terms, factor out the 2, and it's this 2 that has that sort of direct relationship to our delta value by way of our epsilon value. That's the 2 that we're dividing epsilon by in order to arrive at a delta value of 0.05. In other words, we stay within 0.1 in the y direction as long as we stay within 0.05 in the x direction. If you're thinking to yourself, I do not like this, if I were there with you, I would say, I believe you, and I don't blame you one bit. If we change that epsilon value from a 0.1 to a 0.01, then we would need to divide by 2 again, and our delta value would become 0.005. That's what we're saying here. And if we change that epsilon value to a 0.01, then we would have to change delta to half of that, 0.0005. So the narrower the constraints of our output value, the narrower the constraints of our input value are going to need to be. And the ability to have that little bit of wiggle room is often called error tolerance. But as you can see, an error of plus or minus delta in the x direction can cause an error of twice that in the y direction. So it's very important to know, especially imagine if it were a medication, if there's a little bit of variety in the actual chemicals that are in a particular medication, if there's a little bit of variety there, could it cause maybe a very large swing in your blood pressure or your kidney function or your brain function or whatever it is, right? So this is a very important skill to be able to have in a lot of different industries. The real-world applications here are enormous. So here we're seeing it all entirely symbolically. We're seeing here's the constraint, which was originally 0.01, and here's our delta value being set equal to the 0.0 or the 0.1 divided by 2. Now again, everything that you're seeing on the screen here is still directly related to this first example problem, where our epsilon was 0.1 and our delta value ended up being half of that. Here we're seeing a graphical representation of this same problem that we're talking about. Notice on this graph that we have our x value was approaching 3, right? This said the limit as x approaches 3 of our function f of x was equal to 5. So the 3 that you're seeing here is here. The 5, which is capital L, that's here. Here's our plus or minus epsilon, that's the wiggle room in the y direction. And here's the constraint in the x direction that keeps us within those y value boundaries. When it's a linear equation, the diagram looks really nice like this. That very first diagram that we saw that had the curve in it, different situation. We had to choose the lesser of our two potential delta values. But when it's a linear equation, you can go right at it. So we are now, after looking at an example with real numbers in it, we have made our way toward an ability to state and maybe better understand the precise definition of a limit that says we can write this, we can say this, but only if, no matter how small we make our epsilon values, our constraints in the y direction, no matter how tightly we confine those y values, as long as we can still find a delta value to land us in that wiggle room of y values, then we're allowed to say this limit statement. So we can say the limit statement if, no matter how tightly we constrain the y values, we can constrain the x values to keep us landing in that neighborhood. And this is just the mathematical way of saying this, pretty much. All right, that's the precise definition of a limit. Congratulations. Here's another way to phrase that. And you're welcome to read that or screenshot it, or if you have access to our WebAssign course, you can print that page out by logging into WebAssign and going down to the resources near the bottom left, clicking into our book and accessing the PowerPoint slides. Here's another way to write it and another way to phrase it. We can take an absolute value statement like this one, and since the absolute value expression is isolated on the less than side or the less than side, we can write this as a compound inequality that says x minus a is less than delta, and then we take that same inequality symbol and we take the opposite of the delta, we put it over here and make it negative delta. So that's where this expression came from. And then if you added a to all three of those regions, as I like to call them, then you would get this second statement. So a bunch of different ways of phrasing the same thing. You don't need to know all of those ways, you just need to pick a way that makes the most sense to you. So if you were already good, don't read the rest of those slides. If you were confused, read one of those slides every 5 minutes. Don't read them all in a row maybe, or it'll make your head spin. Alright, being reiterated yet again there. Here's a graphical interpretation of taking our x values that are near our a value and mapping it over into the range. I don't love that one. This one is considerably better. Right on the left hand side of the screen you can see our starting neighborhood of x values that are within plus or minus delta, and you run them up here through our function and your output values land in the range, and we want to keep that range tight so it's only within plus or minus epsilon of our limit value. This is probably my favorite illustration of what it is that we're really trying to achieve. We're trying to find this delta so that this portion of our domain over here fires us off here through our function and lands us in the correct portion of the range over here on the right-hand side. This illustration would facilitate the same conversation that we very first started off with, except there are no numbers. Right, all I have to do is make this epsilon value 0.5, and this one is also 0.5, and then I come down here and I make this difference here the 0.4, and I come down here and I make this difference the 0.8, and we're having the very same conversation that we started with at the very beginning of our video. So if now would be a good time for you to go watch those initial 8 minutes again, now might be a good time. Just take note of where we are, like right at the 26-minute mark, and then come back and we'll keep chatting. Just a nice little chat. Right, so here's what I just started drawing. So remember, if you choose the 0.4 instead of the 0.8, it overly tightens your constraints in the x direction, but that's a good thing because it guarantees that you're going to land in the correct portion of your y values, your range values. And here we've constrained delta even more. This conversation is involving an actual specific function, which is nice. And so this just goes on to continue marching through some illustrations where we're constraining the y values and demonstrating that the chosen x values do indeed land us in that correct portion of the range of y values. It's worth mentioning here that given this particular function, y equals x to the third minus 5x plus 6, if we're told that our epsilon value is 0.2, sorry. So we're given this function. We're asked for the limit of our function as x approaches 1. It's a polynomial, so we're able to do direct substitution and determine that the limit is equal to 2. Hey, come on in, have a seat. We're able to determine that the limit is equal to 2. So our x value, our lowercase a value, is a positive 1. The capital L value is a positive 2. We're being told that epsilon is equal to 0.2, so we want to be at capital L plus or minus 0.2. The only thing that we still have to find is our delta value. Here's the graph of our function, and we've changed the window. So if you're using a TI graphing calculator, or if you're in desmos.com, desmos.com, you can change your view so that you can sort of zoom in on the part of the graph that you're most interested in. And in order to figure out potential x values that would land us within this range of y values, if we graph y equals 0.8 and y equals, or sorry, 1.8 and 2.2, those horizontal lines will come over and intersect our curve at these specific points. And those specific points, of course, have corresponding x values that we could come down and find on the x-axis. How am I supposed to find those x values? Well, you would have to take 2.2 and plug it in for y, and then subtract it over to the other side, and this is going to be a really gnarly equation to try to solve once you subtract 2.2 from both sides and have it equal to 0. The easiest way for sure to accomplish that is to use some kind of a graphing utility where you can graph the curve and graph these two y equals 2.2 and 1.8 in this case, and use intersection mode. If you're in Desmos, you can just click on the point of intersection, and then I think if you click it again, it'll freeze it there and it'll show you the x value. If you're on a TI grapher, you'll have to use trace, and then second trace, which puts you into Calc, and then select intersect. Go watch a video about how to use intersection mode on a TI grapher. But that is your best way to get those corresponding x values. Now, of course, this problem is going to give us the corresponding x values. To the left of 1, we had 0.92. To the right of it, we had 1.12. How far are these two numbers away from that sort of ideal lowercase a value of 1? Well, they're 0.08 and 0.12 away from 1. Which of those two numbers do we want to choose to be our delta value? Yet again, we want that to be the lesser of the two numbers. So we're going to select the 0.8 to equal delta. And as long as we stay within 0.08 away from that x value of 1, we will land within the constraints of plus or minus epsilon away from our limit value. Which it's been so long now, I don't even remember what the limit value was. It was 2. Alright, so that is a walk all the way through an example problem of finding a specific delta value given a particular function and a specific epsilon value. And then I'm going to pause right here and we will carry on in a moment. So I was just scrolling through the other slides that are available, and I think this is going to cover it for our precise definition of the limit. And in part 2, we'll talk about left side and right-sided limits, or approaching from the left, approaching from the right. And if you take and you evaluate a limit where you're going to get a result of positive or negative infinity, we'll address those also. And then, as I said in part 3, my plan is to go through and look at some homework problems and some additional example problems. So, see you in part 2. Thanks.